Welcome to Lecture 3 in our continuation of the class on stochastic processes. Today we will focus on the concept of the generator of a Markov process. We had defined a generator of a semigroup already in the previous lecture. Today we will come back to this definition and study some properties of generators of Markov processes or semigroups. And we will identify the generator of Brownian motion and give another example towards the end of an example of a Markov process that we haven't seen so far, which is the so-called reflecting Brownian motion. So let's recall the most important definitions that we need for today's lecture. We start with the definition and repetition of the definition of a Feller semigroup. It starts with a topological space, which for simplicity we shall typically assume to be a Polish space, so it's basically a completion of a countable space. Then we consider a family of operators on the set of continuous functions on that space which vanish at infinity. And this family of operators is indexed typically by the non-negative real line. Could be a subset of that, but for simplicity let's just assume it's the full non-negative real line. Then we call this family of operators a Feller semigroup if the following four conditions are satisfied. First of all, each of those operators is a positive operator, which means that if we feed the operator with a non-negative function, then the resulting output will again be a non-negative function. The second condition is that the transformation which corresponds to time parameter 0 is just the identity operator. The next condition is the semigroup property, which says that the repeated application of two operators at two different times or two times is just as good as if you apply one of those operators only once, where you have to choose as time index the sum of the two previous time indices. That's the semigroup property. And the fourth property is the continuity of these operators, which can be written in a condensed fashion that for any function from our function space, the difference between the perturbation of this function and the unperturbed function when you send the perturbation parameter to 0 is becoming small, is just converging to 0 with respect to the uniform topology, with respect to the supremum norm. If these four conditions are satisfied, we call this family of operators a Feller semigroup. Then we have two additional properties that we sometimes additionally put on our conditions. Namely, one is that we call this semigroup contractive, or a contraction semigroup, if the infinity norm of the output after perturbation is bounded from above by the infinity norm of the input. In that regard, it's each of those operators TT is a contraction operator on our function space, which is equipped with the infinity norm. In this case, the semigroup is called a contraction semigroup. And a stricter condition is that if we call this semigroup contractive if the one function is mapped onto the one function for all time parameters t. The latter condition here has to interpret it in such a way that we find a sequence of approximating functions which vanish at infinity and which approximate from below the constant one function. And then for this limit that we obtain, we see that, or we require that this limit of this one function, or the sequence of approximations to the one function, gives back just the one function. And we have seen that this conservative property, a conservation property, means that the corresponding representing family of kernels is in fact not only a sub-Markovian kernel, but effectively a Markovian kernel. Okay, so these two additional conditions are sometimes explicitly also marked. Sometimes we forget to mention that implicitly we work with these two additional conditions. Typically, most of the cases we will deal with conservative Feller semigroups and will not even mention it. We will implicitly assume that. So whenever you have some doubt whether some result might be true regarding the conservativity, because it wasn't mentioned as an assumption, then it might be the case that implicitly we assume that we're dealing with a conservative semigroup anyway. Okay, so that's our concept of a Feller semigroup. And if we are given such a Feller semigroup, we can associate it to it what is called the generator. And the generator is then an operator on this typically infinite dimensional space of continuous functions, namely an operator, as you learn in functional analysis, on an infinite dimensional space, or hypothetically infinite dimensional space, needs to be defined by first indicating and defining what is the domain of this operator, so on what subset of the functional space that you're dealing with the operator is defined, and then by actually defining the actual assignment rule that comes along with this operator. Okay, so we define the generator in this way of a Feller semigroup as follows. Its domain will be defined by all functions f in our function space, for which we can find another function g, let it be b, let us call it g, another function on function space, such that the difference quotient approximation of the derivative of the semigroup acting on this function f at time t equals 0, that's the difference quotient approximation of the derivative of the semigroup at time equals 0, acting on the function f, if this approximation of the derivative has a limit with respect to the infinity norm, and this limit is g. So if we find a continuous function vanishing at infinity such that this limiting statement holds true when the time parameter t, or the approximation parameter of this difference quotient here, tends to 0, then we say that the function f belongs to the domain of the generator A, and the assignment of the operator value to that function is exactly this difference quotient, or this function g, if you like, which was appearing there as with this name in the previous definition. So, if we have given a Feller semigroup, then by this recipe we define the corresponding generator of that semigroup. It's just a definition for the moment. But we have already seen at the end of the previous lecture that in case of the Brownian motion on Euclidean space, or in one dimension, we can at least say that if a function f has a certain regularity property, namely if it is a function whose first and second derivatives exist and are also bounded, are also continuous functions vanishing in infinity, then such functions belong to the generator of Brownian motion, or to the semigroup which is generated by Brownian motion, is associated to Brownian motion. And in this case, the generator of such a function is the new function, which the function g in this case is plus 1/2 the second derivative of the function f. So example, we had already seen this. Pt is the semigroup for Brownian motion, and in this case, if f is in C20 of the real line, which means its first and second derivatives are also continuous functions vanishing in infinity, then this is in the domain of the generator for Brownian motion, and in this case the generator of Brownian motion is 1/2 times the second derivative of the function. Okay, we discussed this example at the end of the previous lecture. One of the main aims of today's session is to complete this example by not only showing that if a function f has these regularity properties, then it belongs to the generator of Brownian motion, but we also want to give a full characterization of the set dA in the Brownian motion case by saying that if a function is in the domain of the generator of Brownian motion, then it must necessarily have these regularity properties. If we can make such a statement, then we have actually obtained a complete characterization of the generator in the case of the Brownian motion, which is already a little bit of an achievement, because we will have then established at least one complete construction of a generator in one particular case. And we will complete today's session by providing a new example of a new Markov process which you haven't seen so far, which is the so-called reflecting Brownian motion, where we'll use this precise characterization and we'll establish such a precise characterization for this new Markov process. But in order to do this, we need to develop a little bit the theory and provide additional tools which will help us to complete this characterization as follows. And one of the tools is the following proposition, which deals with the differentiability, effectively, of the semigroup as a function in time. Here is it. It says, if we have a Felle semigroup for a general Felle process, as usually defined on this function space of continuous functions vanishing in infinity, and if we have a function f which belongs to the domain of the generator, then for all positive times, the application of the semigroup to the function f also belongs to the generator. Moreover, this function, as a function of time, which assumes values in the space of continuous functions continuous functions vanishing in infinity, this is a function, is a Banach-valued function, which is differentiable in this Banach space, and the derivative of this function is computed as a times ptf, which can also be written as ptaf. So the derivative of this function pops up or brings about the operator a in an explicit fashion. And in case when f belongs to the domain of the operator, the pt operation and the a operation, in fact, commute, so we can write this iterated application of a and pt in any order that we might prefer. And the third statement is that the fundamental theorem of calculus is also true, namely if you take the difference of ptf and f, you can write this, of course, if you use differentiability, as the integral of the derivative, and we have this explicit representation of the derivative which is coming from the previous assertion. And before we prove that, I would like just again to give you this analogy. If you believe in the analogy with towards the finite dimension or one-dimensional situation of the exponential function, if you recall that in this case we write tt times as an e to the alpha t, and then of course what we know is that at any time d by dt tt, this derivative is nothing but alpha times e to the alpha t, which is alpha times tt again. So by analogy with this familiar one-dimensional calculus example, the formula that we have here is exactly this repetition of this formula, and it indicates again that we have this relation that the semigroup tt is nothing but the exponentiation of alpha times t, with the small, if you like, difference that the alpha here again is not a constant but an operator on infinite dimensional function space, typically infinite dimensional function space. Okay, so let us show this, and we just do it by explicit computation of the generator. So let us consider two time points t and s, and let us look at the difference quotient approximation of the operator a, which we plug in or which we apply to the function, which is obtained not by f but by ptf. So what you have here in this on the left hand side of this equality is the difference quotient approximation of the operator a, which acts on the function ptf. Now obviously pt and ps commute because they can be written as altogether they can be written as a one-time application of the operator pt plus s, and that's commutative with respect to t and s, or it's symmetric with the role that t and s are playing. So therefore I can interchange in this iterated application of s and t, I can interchange the two indices t and s, which I did here in this first step. But then I see that I have the operator pt, which appears here to be operating on two different functions, namely a function which is PSF and F. So I can pull out this PT operation towards the front to obtain this expression here. And now I can use the continuity of the PT operator. Recall that PT was assumed to be a continuous operator, so therefore I can pull the limit inside the PT, which is what I do here. But I can do that provided the inner limit exists, right? So if the limit of the interior object, which is plugged into the PT operation, if that limit exists as a limit in this space of continuous functions, then I can pull the limit inside or outside this PT map, because the PT map is by assumption continuous. But finally, I can use the hypothesis that the function f belongs to the domain of the generator A, so therefore the inner limit is known to exist, and it is AF, where A is the generator of the function. So what do I learn? I learn that if I go back to the left-hand side, I learn that the difference quotient approximation of the generator A, or of the derivative of the semigroup, applied to the function PTF, that this difference quotient approximation has a limit, and therefore PTF belongs to the domain of the operator. And I have already also seen that, of course, in this case, the actual value of this difference quotient approximation, or the limit of this difference quotient approximation, exists, and I have computed this limit of this difference quotient approximation, which is exactly PTAF, which is nothing else but saying that A applied to PTF is in fact that thing which I had just computed, it's namely PT times AF. This shows, in fact, that not only PTF, this shows not only that PTF is in the domain of A, which was our claim number one, but it also shows that, in fact, this function PTF is differentiable with respect to the time parameter. Probably I was jumping ahead a little bit of the differentiability with respect to the time parameter, as I forgot. Yes, that involves one more little argument which I shall present now. Okay, so, right, I was jumping a little bit ahead with regards to the differentiability. First of all, this argument that we have just presented shows that this function PTF as a function of t is right differentiable, which is to be understood that if I do a difference quotient approximation at any moment of time t, but from the right, so I do an additive shift of the time parameter t in positive time direction, then this has a limit, and this limit is given as PT of AF. That's a consequence of the previous argument, which is to say that the function PTF is right differentiable, and the derivative of this, the right derivative of this function is given by PTAF. And now I want to make an argument that this function is also left differentiable, or I want to compare with a function whose derivative I do know explicitly, and the comparison is with the function psi of t, which is defined to be the integral with respect to the time parameter s on the domain 0 to t, ps a f ds. So what is that supposed to be? I know a is on the domain of the generator, so this af object is well defined, and I act on it with a semigroup at any time s, but here, for the definition of the function psi, I define, or I choose to consider the time integral of this continuous function, which assumes values in this Banach space with respect to the time parameter s. Then this is a continuous, and even by a fundamental theorem of calculus, is even a differentiable function with respect to the time parameter t, and as usual, I know that for this particular example, for this particular function, I can explicitly identify the derivative through fundamental theorem of calculus as PTAF. Hence, if I compare my function, which I started with, and this psi t function, I can take the difference of these two functions, and I compute the right derivative of these two functions. If I do so, I see that both right derivatives of the initial pt function and the psi function, they coincide. So hence the difference has a zero right derivative. But now I can take the fact that if I have two functions which, for instance, are continuous and have the same right derivative, then these two functions can differ with respect to the time parameter only by a constant, which here in this function space means that these two functions differ only by a function which is in function space, but which in particular does not change over time. And hence I can ultimately conclude that the full derivative of this PTF function as a function in t must coincide with the derivative of the psi function, because the function on the left-hand side differs from the right-hand side as a function of t only by a constant. So therefore, whenever this function on the right-hand side is differentiable with respect to the time parameter, then so must be this function on the left-hand side with that, with respect to the time parameter. And that gives us ultimately the differentiability of the pt function as a function of time. Okay, and ultimately the third assertion regarding the difference of pt, f, and f, and the way to represent this difference as an integral with respect to the time axis, that's in fact just an application of the fundamental theorem of calculus again. We now present the second rather technical result on the nature of this operator, which is the generator of a Feller semigroup. Namely, if we have a Feller semigroup pt on our function space of continuous functions with which vanish at the infinity, and if we have the generator given, then the domain of definition, so the domain of the operator, is a dense subset of the space of continuous functions. The next proposition appears to be of purely technical nature, and it discusses the geometric properties of the domain of definition of the generator of a Feller semigroup. And it tells us that the operator A is closed, which is a concept from functional analysis, and which has consequences which we shall use a little later. Recall that an operator which is defined on a Banach space is closed if the graph of the operator is a closed subset of the Cartesian product of this operator, of this space, which means the following. So if we consider the set of pairs x from the domain of the operator together with the value of the operator in the second coordinate, then this set as a subset of the twofold Cartesian product of this Banach space is closed. So in our example, that would mean that this is a closed subset of the space of continuous functions vanishing at infinity, but the Cartesian product of this. This is a subset of the twofold Cartesian product, and the claim is, or the condition is, that this is a closed subset. So an operator which is defined on a subset of a Banach space is closed if the collection of tuples which are obtained by inserting into the first coordinate an element of that domain of the operator and in the second coordinate the actual value of the operator, if that collection of tuples is a closed subset of the twofold Cartesian product of this Banach space, then we call the operator closed. Okay. And here's the statement again. It says, if we have a Feller semigroup on, in this case, our Banach space of continuous functions which vanish at infinity, then the domain of definition of this operator is necessarily dense, and also the operator is closed. In order to show this, we introduce two operators that we shall use below, also in other arguments, namely the A and an A operator acting on a function f is this difference quotient approximation with parameter h of the actual operator itself. And note that this operator AH is a bounded operator which can be applied to any function f. And also we have another approximation of the identity operator, in fact, which is the operator BS, which is the integral of the semigroup acting on a function f, taken from, with respect to time parameter u, from 0 to s, but divided by 1 over s. So that's an approximation for s tending to 0 of the identity operator, but which involves an application of the semigroup. So that's the BSF operator. And also BSF is a bounded operator which is definable, which can be applied to any function f from this function space of continuous functions vanishing at infinity. Okay, A and B are bounded operators. And moreover, it's an exercise to check that these two operators in fact commute. So AH and BS commute. I can write them in any order I wish. And moreover, I have the property that if I have BS acting on AH, I can also interchange the two indices of approximation. That's a simple exercise that that you can verify your own. That the actual reason for this is that both, and here's again, sorry, there's one misprint here. The next result is of rather technical nature, and it contains information about the geometry of different sets that come along with the generator of a semigroup. It says the following: if we have a Feller semigroup, then the domain, a Feller semigroup on the set of continuous functions which vanish at infinity, then the domain of definition of the generator is a dense subset of all continuous functions. So remember our example of Brownian motion there, the domain of definition for the operator A was those functions which are not continuous, but even continuous including their first and second derivatives. This is a strict subset of all continuous functions, but it's a dense subset with respect to the uniform topology. That is not a coincidence. That's a general property of generators of Feller processes. That's the first part of this theorem, of this proposition. And the second part of the proposition is that the operator A itself is closed. Recall that we call an operator on a Banach space closed if the pair of tuples, which are obtained by taking in the first coordinate any element of the domain of the operator, and in the second coordinate of the tuple the actual value of the operator acting on this element. This set of tuples as a subset of the twofold Cartesian product of this Banach space, this is required to be a closed subset. This collection of tuples is what we call the graph of the operator, and we want that this graph of the operator is a closed subset. The closeness of operators has a lot of functional analytic consequences, for instance, Fredholm alternative and other things, and we will make use of these consequences from time to time. But this proposition here is also of value in the sense that it brings about certain constructions which are helpful for the subsequent conclusions. Okay, so in order to prove these two assertions, we introduce two other operators which are allowed to to make concise arguments. The first operator that we introduce is this AH operator for a positive parameter h applied to a function f. This is exactly this difference quotient approximation for approximation parameter h acting on the function f. And the second operator we want to introduce is, we'll have the name b with a parameter s, it's just a name, and it's an approximation of the identity, but by means of this semigroup. We integrate the operation of the semigroup with respect to the time parameter on the interval from 0 to s, and we divide the whole thing by the length of this interval. That's another operator we might define by using the semigroup P. Now, both operators AH and B just involve a finite, if you like, constructions and finite convex combinations or so of this semigroup PH. So therefore, both are bounded operators on this function space, so they can be applied to any function. They also commute. And finally, it is also so that if we write BS and AH in such an order, then we can also interchange the two regularization indices H and S in the definition of the two operators A and B, respectively. The fact that these commute and they can make this swap of H and S parameter in this equality is basically a consequence of the fact that this operator, or that these semigroups P commute. So what we know is that PS after PT is the same as PT after PS. That's just true because in both cases this is just P at the evaluation at T plus S, which is commutative obviously in T plus S, or symmetric in T plus S. So therefore we have this commutation rule for the semigroup, and that implies also that we have these commutation rules for these two operators A and B. Now, let us pick a function from function space and choose S positive. And let's take a look at the approximation of the difference quotient of by means of this AH operator. So if we consider this limit, then this limit, this object behind the limit by the previous commutation rule can also be written as an AS after we do the BH operation, where the limit is here outside. And if we look at this, since AS is a continuous operator, again we can move the limit with regards to the H parameter inside the AS operation. And if you take a look at the definition of the BH operator or BS operator, this is just an approximation of the identity. This BSF thing is basically a smoothing operation by means of the kernel, which converts every function f into a smoother function by doing a little bit of smoothing by means of this heat kernel or by means of this semigroup. Okay. Ultimately it says that, or here in this context, it means that the BH, if I send H to 0, converts to F alone, and therefore I find that this limit on the left-hand side exists and has this representation, which in particular by definition of our operator implies that BSF is in the domain of H. But again, if we send S to 0 by the argument that we had just described verbally, if I send S to 0, then BSF converges to F in the norm on continuous functions, in the supremum norm on continuous functions. And hence we have constructed, for that arbitrary function F, we have constructed an approximation by other functions, which in this case are called BSF, which all belong to the domain of the operator A, and which, as we have just said, approximates the function F. So therefore, for any function F, we find a sequence or a family of functions which converge to that function F, and where each element of the sequence belongs to the domain of the operator A, which means that the domain of the operator A is dense in our function space. Now we show the closeness of this operator. What we have to show is that if we have a sequence of points which lie in the graph of this operator, then, and this sequence converges to some element in the Cartesian, twofold Cartesian product of this Banach space, then this limiting element will also be an element of the graph of the operator. So what we have to show is this. So if we have a sequence of points in the graph, which is here said to be said that if we have a function, a sequence of functions which belong all to the domain of the operator, such that they converge to some element with respect to the supremum norm, to f certain element f, and if also there is a continuous function such that the collection of values of the points fn under the operator converge to that function g, then we want to show that f will also be, so the limit of arguments will be in the domain of the operator, and we want to show that this limiting of the second coordinates, that g is in fact the actual value of the operator applied to that limiting argument argument. Okay, so let us fix this sequence of fn elements, of which we know that the fn's converge to some f, and of which we also know that afn converges to some g. So what can we say about the g? Well, we take our B operator, the approximation of identity, and apply it to the G. Then, by continuity of the BS operation, the G, as we know that the G is the limit of the AFNs, we can write the G as the limit of the AFNs, and then we can take the limit outside of the B, because the B is a continuous operator. Next, we know that the AH operators are an approximation of the A operator. And the FNs are in the domain of the operator A. So for each n, I can write the AF, the AFN as a limit with respect to an H, with the parameter H approximation of the A operator by means of these regularizings or these difference quotients. And now again, by continuity of the B operator, I can pull this limit with respect to H in front of the B operator. That's what I do here in the next step. So I pull this limit outside of the B. And then I have, outside of the sequence of operators, I have the twofold limit with respect to the N and the H parameters. And then I have, after this limit, I have BS applied after AH. But then again, I can use my commutation rules, and I can write the AS first outside and inside the Bn, which is just this swap of parameters. But now the Bn's are an approximation of the identity. So therefore, this first limit with respect to the n operation just gives me the B, and I can forget about that. And I'm left with the n limit of the AS. Correction, there is a little bit of a mismatch here. Let us now show the closedness of this operator. For that purpose, we have to consider the case of a sequence of functions fn, which all belong to the domain of the operator, which converge to some function f, and whose images under the operator converge to another function g. What we have to show then, in this case, is that f belongs to the domain of the operator, and that g is, in fact, A of f. That needs to be shown. Okay. For that purpose, we consider the BS operator applied to this limit g. Okay, BS is a continuous operator, so therefore knowing the fact that g is the limit of the AFNs, we can also replace this g function by the limit of the AFNs, but for the continuity, or due to the continuity of the BS operator, that limit can be taken in front of the BS operator. For the next step, we recall that the operator A can be approximated by a sequence of bounded operators AH. Hence, for each n fixed, A of Fn can be written as the limit with respect to this approximation parameter H as this AH of F. Now we use again that B is a continuous operator, which allows us to write the limit with respect to this H parameter in front of the B. And what we are left with is the consecutive application of BS and AH after those two limit operations, but by the commutation rule that we had discussed at the beginning of this proof, we can also write this as a composition of AS applied after BH. Now, AS is a bounded continuous operator, so therefore we can move now the H operation inside the AS, but we had seen that the BH operation converges to the identity operator when H tends to 0, so hence we have here the AS operator after we take the H limit acting on the Fn function alone. And finally, the AS operator is a bounded operator. The Fn's converge, as we know, to some function f, so therefore if we put the limit inside the AS, we get the AS of f. So hence we know that for any positive s, Bs of g is As of f. Okay, we know since Bs is an approximation of the identity, that Bs for s tending to 0 converges to g. In particular, the left-hand side has a limit in our function space, and therefore the right-hand side must converge, which, since As is an approximation of is the difference quotient, which just entails that f is in fact in the domain of the operator. Moreover, by passing through the limit, we see exactly that g is exactly the operator applied to g. So hence we have proved exactly what needed to be proved in order to show that A is closed. We now present the last part of abstract theory of semigroups, which we will use for the full identification of the generator of Brownian motion. For that purpose, we introduce the following important definition. For lambda positive, we introduce the operator R lambda, which is again a bounded operator on function space, and if I have the application of R lambda to a function is defined as the infinite integral with respect to the time parameter or S parameter of the semigroup, but weighted with an exponential decaying factor e to the minus lambda s. So for each s, I apply the semigroup ps to the function f. I multiply with this exponentially decreasing prefactor, and I integrate the whole thing with respect to this s parameter along the full positive time axis. This is, as you convince yourself easily, is a bounded operator on function space, and it's called the resolvent, the lambda resolvent to be precise, associated to this the semigroup. It resembles, in its structure, it resembles a Laplace transform, which is just taking exactly this integral over a certain function psi. So assume that we replace this thing by, if we were just in one dimensions, we could replace this symbol or this notation here by some function phi of s, which is a real valued function. So if we consider the integral from 0 to infinity e to the minus lambda s ds, this would be exactly the Laplace transform of this psi function evaluated at the position lambda. So we see that this resolvent operation is basically a Laplace transform of the semigroup with respect to the time parameter. Okay, that's the resolvent operator. And for each lambda positive, we can define this resolvent operator. And here comes the important proposition which we shall use for the full identification of for instance, the generator of the Laplacian, of the Brownian semigroup. So fix any lambda positive. Then we can take a function f from the domain of the operator and map it onto lambda f, so just a multiple of f, minus the generator of the semigroup applied to the function f, and we take the difference of these two things. So lambda of f minus af, that's a certain operation. And by definition of the domain of the generator A, this is an admissible operation, so A of f is well defined. In this case, this gives back a function which is in our function space of continuous functions vanishing at infinity, and in particular this linear combination is also in this space, so therefore this object here is well defined as an object in our function space. And the proposition says now that this operation, which maps a function onto this new function, that this is a bijective map whose inverse is exactly the lambda resolvent. So this says, though, the statement that the resolvent is the inverse of this operator leads sometimes to the shorthand notation for the R lambda map. R lambda is then often informally written as 1 divided by lambda minus A, which is, of course, since A and R lambda minus A, well, it has to be understood in what sense this is an invertible map, but once you have clarified, and it's part of the statement here of this proposition, that this map is in fact invertible, it has full range, that's also, it has full range, and it has an inverse which is exactly the resolvent. So therefore this notation is justified. Okay, this notation is a consequence of the proposition, and we will now show this proposition, which is very helpful for the identification of the domain of the generator of a semigroup. Okay, we want to convince ourselves that if we apply this R lambda after we did the lambda f minus AF, that this gives back the f. This is one part of the identification that R lambda and this operator that we had written here, that these two operators are the inverses of one another. So let f be function from the domain of the operator, to the generator. Then let us write down R lambda, this resolvent, applied to the functions that is obtained as lambda f minus AF. When by definition of the resolvent, this is this infinite time integral, where now this infinite time integral involves a sum of two integrands. So therefore we decompose this infinite time integral into these two different summands. Well, if we take a look at the first part, this is unchanged in the transition to the next line. But if we write down what this AF guy means, well, we have seen in basically the first of our propositions that AF, so what we have here, so let me put the PS in front of the A. So then what we see is that PS after A can be written as the time differential of the PS semigroup, of the P semigroup evaluated as. So therefore we can replace the PS of A as the d by ds PS, the time derivative of the P function, or the P operation. But here we have now, inside the second integral, we have now an operation which calls for an integration by parts, because here we have some function which depends on s, and here altogether we have another function which depends on s, but it's not the function which is written here, but its derivative. So we can try to perform an integration by parts by mapping the time derivative onto the first function. And what we obtain is, of course, the boundary parts of this integration by parts, which will be e to the minus lambda s psf, evaluated for s equals infinity, where the e minus lambda infinity produces a 0 for the evaluation at infinity, minus the evaluation of this e minus lambda s ps at s equals naught, which gives just the function f back. And then we have to subtract the corresponding integral, where this ps derivative, or the derivative operation, is mapped onto the first factor. And here the derivative of the first factor produces a plus lambda, in front, so that we are left with this expression here. So that by we differentiate, we move the differentiation towards this function on the left-hand side, this left factor, and this gives me a minus lambda times e to the minus lambda s, where lambda is, of course, then only a factor which can be moved out of this integration. And if we compare the terms that are showing up here, we see that these now resulting time integrations exactly cancel due to the right sign that we have in center front, and what is left alone is what is left over is exactly just the function f. So this computation shows, in fact, that if f is in the domain of the generator, then doing this lambda f minus af first, and then the resolvent gives back the f function. So therefore, the r lambda is something like the left inverse of the operator which we had before. And conversely, if we now would like to show that this operator lambda identity minus a is the left inverse for the resolvent, we take an arbitrary function from our function space, we apply the resolvent to that function, and we want to apply the operator a, and since we want to be a little cautious, we just do not apply the operator a, but we apply the difference quotient approximation of the operator a. Then, since the difference quotient operator deals with the semigroup alone, it's easy to see that this AH operator commutes with the resolvent operation. And now if we write down what that means, well, the limit in h to 0 is in front, and then we just write down again the resolvent of this, the resolvent acting on this difference quotient approximation. This is our AH of f, and we need to do this resolvent transformation by means of the action of the semigroup PT. Well, and here again we can probably write this as a sum of two integrations which involve an integral over the full time axis, where one of the two integration involves the semigroup after I use the semigroup property at time position t plus h. So I can accommodate for that by doing an additive time shift with respect to an h within this h parameter that will be put into a change of parameterization. So the first time integration, okay, so I should probably say this 1 over h factor goes in front of both integrands because it's a joint prefactor. And then, as I just said, the first of the two integrations after I use the semigroup property for pt after ph, which is in fact a pt plus h, I perform an additive shift with respect to the time parameter to have this representation of the first integrand of the first integration, and the second integration is remained unchanged. And this is now, I see that this is something like a differentiation of an integral which depends on this h parameter in two different ways. And then if I do the limit or I do the differentiation of this expression with respect to the parameter h at h equals 0, I arrive at this representation of the remaining integral. And if I look at the terms which are left here, these two terms, I recognize that this is the resolvent again acting on the function f minus f alone. What does that show? Well, it shows that, of course, first that the resolvent maps back into the domain of the generator, because the limit on the left-hand side that we started with, or the limit of the expressions on the left-hand side that we start with, exists. And we also can compute, as actually we have an explicit knowledge about the actual value that we obtain once we apply this generator A to the resolvent of f. Then it's just lambda r lambda f. This is what we have here. So it's the resolvent times lambda. I probably forgot to say just a few seconds before. So it's lambda times r lambda f minus f. And this tells us, if I rearrange this equality, it tells me that if I apply the operator A minus lambda identity to the resolvent or in other words, if I apply lambda, I rearrange this equality which I have just established. I solve this inequality, if you like, for f. I put f on the left-hand side and I subtract a. Then this, if I write this corresponding equality here, then it means that lambda minus the a operator, lambda times identity. So lambda times identity minus the a operator applied after I do the lambda of f, then this gives me the f back. This is what is written here in shorthand notation. Lambda minus identity after a resolvent gives me back the it gives me back the initial function that I started with. So altogether, together with the conclusion of the first part of this proof, I have now altogether that R lambda is the left inverse of this operator lambda minus a, which is defined on the domain of a, and I have that lambda minus a applied after the resolvent gives me the f back, or in other words, lambda minus a is the left inverse of the operator R lambda. So in particular, R lambda and lambda minus a are the mutual inverses of one another. So here is lambda minus a. That should have been written like this. Now this in particular also implies the statements about injectivity or bijectivity, in fact. Since the resolvent is defined on every function, it tells me that that the full range of this lambda minus a operation is the full set, and it also tells me that these two maps are in fact bijective. After these preparations, we now can come back to the part of the characterization of the generator of Brownian motion, which was not done, which is to show that if we have a function which is in the domain of the generator of Brownian motion, then it must necessarily have this regularity property, namely that it's not just a continuous function which vanishes at infinity, but that it also has first and second derivatives which are continuous and which vanish at infinity. And recall again that this implication or this direction was shown at the end of the last session, when we showed that if we have a function of such regularity, then it is in the domain of the generator of Brownian motion, and the generator applied to such a function is then just 1/2 the second derivative of that function. Okay, now we want to show that if we have a function which is in the domain of the generator, then it must have this regularity properties. And if we know that it has this regularity properties, then we already know that the generator applied to this function is this second derivative times a factor. Okay, and for the conclusion, which we want to do, we now use the theorem or the proposition which we just have established, which told us in particular that any function from the domain of the generator of the Felice semigroup can in fact be written as the resolvent of a suitably chosen function g in the function space. Why is this so? Because we have seen that the resolvent operation is an inverse of an operation whose domain is the full domain of the generator. So therefore, every function which is in the generator can be mapped into this operation that we had before, and then we can go back via the resolvent, which in other words tells us that there is a certain function g, and as a matter of fact we can even write it explicitly, but it doesn't really matter so much. We know that there is a function g whose resolvent transformation gives back the function f, and the function g is some function of our function space. Now, hence we write f of x as this resolvent evaluated at the position x. But in the Brownian case, we have explicit knowledge about the shape and about the nature of this resolvent, because the semigroup here in the Brownian case is explicitly known. It is the semigroup induced by integrations against Gaussian kernels. So Pt of g evaluated at x has exactly this representation via a weighted integral, which involves the Gauss weighted integral of the G function, which involves the heat kernel. There is a minus missing, of course. Okay. And now it's a standard example from analysis. Well, analysts know this kind of construction. They call it the mollification by a standard mollifier. We know, or you can check yourself, that if you take any bounded function, for instance, bounded measurable function g, and you do this integration of g against the heat kernel, which then ultimately is a function which only depends on the exterior parameter g, that this gives, even for measurable functions g, gives you for positive t, gives you a function which is infinitely integrable, infinitely many times differentiable. So this function ptg as a function in x is automatically even a infinitely many times differentiable function. So it's a smooth function on the real line. So therefore the existence of first and second order derivative of this function f, which has this representation, is not, this question is clear right away. And we have made this conclusion by exploiting the fact that the function f, which we consider is not an arbitrary function, but is a function in the domain of the operator, which allows us to write this function as the resolvent of a suitably chosen function. Well, okay, I was one step ahead. At the resolvent, so the semigroup at any time t is a smooth function, the semigroup applied to infinity function g. What we have here is slightly more complicated because we do still a weighted integral with respect to this exponential weighting factor. But if this is a smooth function in x for all t, then also this integral of the additional t parameter gives a smooth function in x. Okay, we have an explicit representation also for the derivative, which is then just a derivative of this integration of this parameter-dependent integral with respect to the exterior parameter. Note again that the integration here is done with respect to the y variable, and the exterior parameter is this shift parameter, which is in the top of the exponent. So even then, also by some standard theorems of measure theory, integration theory, we can see that this is a differentiable function with respect to x, which is differentiable with respect to the parameter. That's obtained by some dominated convergence theorem or something, and we can convince ourselves that this is the right representation of the derivative. And likewise, we have an explicit representation of the second derivative, which is just doing a parameter differentiation of this interior function here, of this weighting function, another time with respect to the x variable. So therefore, we obtain this representation for the second order derivative of this function, which is a smooth function for any even bounded function g. Okay, so therefore, and so if we additionally use the fact that the Gaussian kernels are exponentially decaying for large exponential weights, we can convince ourselves easily that if the function g is vanishing at infinity, so it's something like almost zero outside a sufficiently small, outside a sufficiently big compact subset, then this property will not be destroyed if we have these exponential weighting in front. So I'll leave it as an exercise to show that as a consequence also ptg is a C2 function which vanishes at infinity for all positive time t, and I also leave it as an exercise to show that as a consequence, if we do this additional time integration with respect to time parameter, together with an sufficiently fast decaying exponentially decaying weighting factor in front, which guarantees that this whole integral as an integral with respect to time converges, then this implies that also the whole resolvent on such a function g is in fact a C2 smooth function which vanishes at infinity. So that's a little bit of an exercise, but I'm convinced that you can do that on your own. So as a consequence, our function f is in fact in this smoothness class, which was left to be shown. So hence, if f is in the domain of the generator, then it will be have this smoothness, and we already know that on functions which have this smoothness, the generator of Brownian motion looks like this. Okay, this concludes probably today's session. Let me recapitulate what we did. We started out, we had finished last lecture with a partial characterization of the generator of a Brownian motion on Euclidean space, on the Euclidean line. And what we wanted to achieve in this session is a full characterization. And for the purpose of this, we were investigating some mapping properties of a generator of a Feller process in the general case, and as a highlight theoretical result of today's session, we had this relation between the resolvent, which is the Laplace transform of the semigroup for a given parameter. We had this relation between the resolvent of the semigroup as the inverse of the operation that takes an element from function space into this linear combination of identity and the operator A itself, provided the function itself is in the domain of the generator. And this allowed us finally to give a full characterization of the domain of the generator of real Brownian motion.